Alright, let's put all of this into practice. We're going to put the single regressor tests into practice for multiple regression models, and we're going to put the joint hypothesis test into practice for multiple regression models. And we're going to look at R squared. So here what we're going to do is we're going to select the best model, select the best regression model. Suppose we're interested in the effect of class size on test scores. You're working for the school district and they come to you and say, should we invest in reducing class sizes? Should we put some money into making class sizes smaller? And so they ask you to estimate this relationship, where you decide the best way to do this is to estimate a regression model where you're regressing test scores on student-teacher ratios. And then you're going to potentially add some other stuff here. Our goal is an unbiased estimate of the coefficient on class size holding other variables constant, right? So in the extreme case, if this beta 1 is biased in the single regression model, and beta 1 says that student-teacher ratios have a large effect on test scores, then we're going to put money into class sizes when we shouldn't necessarily. So we want an unbiased estimate of the coefficient on class size. What do we need for an unbiased estimate? We need the expected value. Let's write the error term in here. Expected value of the error term conditional on student-teacher ratio is equal to 0. So we need to know that whatever we've included in this regression model means that we're satisfying OLS assumption number 1. So how do we choose which variables to include in our model? That's the question we're trying to answer in this lecture. And then we need to think about this problem before you sitting down at our computers. Okay, so the general approach is we want to specify a base model. We already did this. We thought the base model is test scores as a function of student-teacher ratios. This is the model we might think is correct. Then we're going to specify a range of plausible alternative models, which might include additional variables or logging variables or other methods. And we'll talk about more methods in future modules. And then we're going to compare the models once we've estimated them. We're going to put them in a nice table and see them next to each other, and then we can think about which model seems to be working best. We'll ask questions like, does the candidate variable, in this case, does the coefficient on the candidate variable, beta 1, change when we add additional regressors to the model? If so, why? Might there be omitted variable bias? Is the additional candidate variable statistically significant? If not, what does that suggest? Important. Don't just try to maximize R squared. So R squared is a metric that gets thrown around a lot, especially with people that maybe have just taken a single statistics course. Maximizing R squared doesn't really tell us anything about the relationship between X and Y. So don't add all possible variables to the kitchen sink regression and drop all non-significant variables. That doesn't help us either. So let's look at what does R squared actually do? A high R squared or adjusted R squared, remember this little bar here is the adjusted R squared, means regressors explain variation in Y. The bottom line is this is all the R squared does. It tells us that how much of the variation in Y is explained by the regressors. A high R squared or adjusted R squared does not mean that you have eliminated omitted variable bias. So you still could have a biased coefficient. High R squared or adjusted R squared does not mean that you have an unbiased estimator of a causal effect of beta 1. High R squared or adjusted R squared does not mean that the included variables are statistically significant. This must be determined using hypothesis tests like the t-stat or the f-stat. If the R squared or adjusted R squared increase after adding a regressor, it doesn't mean that the added regressor is statistically significant. Again, basically the same thing. R squareds do not tell us anything about statistical significance. High R squared or adjusted R squared does not mean you have an appropriate test of regressors and vice versa. So that was, we relegate that to the f-stat. What do R squared and adjusted R squared actually tell you? Well, it tells you how much of the variation in Y is explained by the x's, and it tells you that your included variables are potentially good predictors of the dependent variable. So it could be the case that your included regressor is just a proxy for something else that it's correlated with. And in fact, the included regressor is not the thing that's actually determining why. Alright, reporting regressions and picking between models. Example 1. First, you want to figure out if your variables make sense to put into the regression. So let's make some scatter plots. What do they look like? So the first thing you really want to do is look at your data. You want to plot the data, you want to look at summary statistics, you want to figure out what should you expect from your data in your regression. So let's consider the test scores on student-teacher ratios and percent ESL. And we're going to add two new variables, the amount of students, the percentage of students on reduced price lunch, and the percentage on income assistance. So these are two new variables we're adding to this problem. So let's look at the relationships between test scores and percent ESL. So this is percent ESL. This is percent on reduced price lunch. I don't know how we write this, but maybe like that. And this is going to be the percent qualifying for income. So we'll call that percent inc. So look at these scatter plots and decide beforehand what you expect the coefficients on these variables to look like. Well, if we drew the best fit line in the first plot, it would probably look something like that. So the slope here, slope is less than 0. It's negative. Again, draw the best fit line. Slope is less than 0. So we should expect these the coefficients on these variables to be negative. Likewise, the slope on this one should be less than 0. So if we find that our coefficients are positive, then we know something fishy is going on. Let's consider the baseline model of just test scores on student-teacher ratios and then compare outputs to different models. So the first thing we did is we plotted the data and we look at it and we say, is there an obvious relationship between these variables? Then we're going to specify our baseline model, the single variable model, and we're going to compare it to models with additional variables. So we're going to have, in the next slide, I'm going to show you a table with 5 columns. Each of the columns represents a different regression output, and these are the models for the regression outputs in the different columns. So column 1 is just going to be the single variable case. Whoops. Column 2 is going to be the case with student-teacher ratio and percent ESL. So let's look at that real quick. Column 1 here is the single variable model. We have an intercept and we have student-teacher ratios in the model. Notice that everything in here is left blank because it's not included in the model. So this is the output that we've been looking at for the class so far. This is test scores on student-teacher ratio. We get a coefficient on the slope, or the beta 1, the slope coefficient of negative 2.28 with a standard error of 0.52, and we get an intercept of 698.9 with a standard error of 10.4. Our standard error of regression is 18.51. Our adjusted R-squared is only 0.49, or 0.049, so 4.9% of the variation in test scores is explained by student-teacher ratios, and we have an n number of observations of 420. Now let's compare that to the second model where we include percent English learners in the model. So, whoops, let's go back one slide. So now we're on the second model here, column 2, test scores as a function of student-teacher ratios and percent EL. We've already talked about this model, but let's look at it in this table. So we have a coefficient on student-teacher ratios of negative 1.1. We said that in one of the previous lectures, we said that by adding percent ESL to the model, we are eliminating some of the omitted variable bias in model 1. Notice how the coefficient on student-teacher ratio comes down in magnitude when we add percent English learners to the model. And you can see the coefficient on percent English learners right here. negative 0.65. With a standard error of 0.031, 2 stars means it's statistically significant at the 1% level, or 99% confidence level. Let's look at some of the model fit statistics. The standard error of regression goes down a bit relative to model 1. That's good. And the R squared goes up. So we jump from 0.049 to 0.424, meaning that adding percent English learners to this model means that now we're explaining 42% of the variation in test scores with these two variables. So that's doing substantially better than we were in the previous model, and we've eliminated some of the omitted variable bias from model 1, and our coefficient on student-teacher ratios is still statistically significant at the 95% level, or 5% significance level. All right, let's compare this to model 3. What is model 3? Model 3 is adding percent lunch. So we keep percent ESL in the model, and now we're adding percent lunch, and we're seeing how that affects our coefficient of interest. So remember, our primary coefficient of interest is student-teacher ratios. We want to see how much does adding additional variables to the model affect the coefficient beta 1, the coefficient on student-teacher ratio. We're primarily interested in getting an unbiased estimate of the relationship between student-teacher ratios and test scores. Notice that adding in column 3, we're adding percent subsidized lunch, the percent of students on subsidized lunch. Notice that the coefficient on student-teacher ratios is really not changing all that much from column 2. So this suggests that just adding percent English learners reduced much of the omitted variable bias from column 1. And so adding an additional control variable does not eliminate much more omitted variable bias, meaning that perhaps we're getting close to this true relationship between student-teacher ratios and test scores. Or in other words, perhaps we're getting closer to an unbiased estimate of student-teacher ratios. In addition, percent on subsidized lunch is negative, as we expected, and it's statistically significant. And percent English learners remains statistically significant. The other thing is that the adjusted R squared goes up, and the standard error of regression goes down. And so now we're explaining 77% of the variation in test scores with an even smaller standard error of regression, so we're doing even better. So this is definitely the preferred model over model 2 or model 1. Okay, what about model 4? Model 4 is adding percent on income assistance. So we're replacing percent on subsidized lunch. We're replacing percent on subsidized lunch with percent on income assistance. And we're seeing how these two different variables affect our regression. Okay. The coefficient on student-teacher ratios, this still remains in the ballpark of the coefficient. So here we're talking about negative 1.31. It remains in the same ballpark as that coefficient in models 3 and 2, so it's not really changing much. And our R squared goes down a little bit. Our standard error of regression goes up a little bit. We get a negative coefficient on the percent on public income assistance, which is what we expected from the scatter plots. And so these two models are similar, but maybe 3 is a little better because the R squared is higher. The standard error of regression is a little lower. The coefficient on student-teacher ratios is a little more significant and lower in magnitude, a little more conservative, and so I would choose model 3 over model 4 in this case. What about model 5? Okay, model 5 is adding everything. It's the kitchen sink regression. We're getting essentially the same results as we did in model 3. So notice that the R squared and the standard error of regression are the same as model 3. The coefficient on student-teacher ratio is essentially identical, a little less statistically significant. And the key difference here is that we have these two variables in the model, whereas in model 3 we didn't have percent on public income assistance in the model. notice that only one of these variables is statistically significant. And this is getting back to the imperfect multicollinearity. So percent eligible for subsidized lunch is essentially the same thing as percent on public income assistance. It's likely that anyone that has public income assistance is also getting subsidized lunch, and so these two variables are highly correlated, and so including both of them in the models really doesn't do anything for us. And in fact, we can't identify both of them simultaneously. Notice how the coefficient on percent income assistance is positive and statistically insignificant in Model 5, whereas we know it should be negative from the scatter plot. So this is telling us that Model 5 is actually adding too many variables. And so the best model in this case, we're now back to Model 3. That's the best model for the relationship between test scores and student-teacher ratios. Okay, so let's summarize all of this. What did we learn? The coefficient on student-teacher ratio goes down after we include the omitted variables, down in magnitude. This suggests there's omitted variable bias, but beta 1 is not very sensitive to which included regressors we have. So beta 1 does not change much from Model 2 to Model 5. It means that the remaining included regressors can each solve some of the omitted variable bias problem. Student characteristics are good predictors of test scores, and student-teacher ratio by itself is not very good at all. We saw that from the R squared in column 1 relative to the R squared in the remaining columns. The signs of the coefficients are consistent, but note that this does not mean that student-teacher ratios is not a bad or not an important variable. Just because it doesn't explain much of the variation in test scores does not mean it's not an important variable. The signs of the coefficients are consistent with patterns seen in the scatter plots. That's good. Like we saw in column 5, when we add both of the last two variables, one of them becomes positive. That's not good. And again, column 5, the coefficient on public income is insignificant and positive, and this suggests that adding it to the regression is redundant. So we want to choose either public income assistance or percent eligible for lunch, and we said that we were going to go with Model 3 for that.